Looks different.
Happen. I think we're live. All good?
Oh.
Check. Uh, yep, we are live. Let's do this.
All right. Hello and welcome everyone to today's brand new episode of Corecast. I am your host, Tim.
Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to it. So without further ado, let's get to it. So Tim, Mikey, this episode actually came out of our previous episode that we did 2 weeks ago about essentially there being a special place in time. And I think that motivated the discussion. Can there also be a special place in like space in terms of as we call it, the singularity? And definitely want to cover more about that. So maybe it might be helpful to kind of, I guess, Tim, I want to point this to you to essentially like give a high level definition of like the connection in special places and singularities. I'm sure people have some preconceived notion of what singularity means and why does it even matter. So why don't we start off with that?
Yeah, I would say, I guess mathematically, generally, if you just have some mathematical objects, you can ask, what's so special about those objects, right? Generally, because math can get complicated, it's really hard to figure out. Like imagine you have like a function, like high school mathematics. You draw a plot of something. You can try to identify special points on this function. Maybe it goes up or down, left and right. But even then, it's hard to justify why certain parts of that function is special. Yeah. But one thing for sure, I'm sure, like if for the audience who have played with your calculator, sometimes the calculator will tell you when something really special is happening. For example, if you ever try to divide 1 by 0, you see that the calculator is like, not happening, right? Or if you try to multiply really large numbers on a calculator, it might give you another error that it's overflowing or something. So I would say, like, of course, singularities are not the only interesting things about a mathematical object, but we'll define singularity a little more precisely. But what we mean is when you have a mathematical object, and when that object breaks, like it no longer makes sense, I think we can safely say that that's pretty damn special. And I think in physics,
we're talking about the concept of infinity, right? Like that, so that's, yeah, like we can people like to think of infinity as an extension of large, right? Like you get really big, like, when you're a kid, you're like, oh, like, like backsies times 2, backsies times 10, backsies times a googolplex, backsies times infinity, and then that wins, right? Like, it's kind of on that spectrum, but like mathematically, it's quite something different, isn't it, Tim?
Yeah, well, I would say singularity is a little more general, right? Like, that's, of course, when it goes infinity, it's singular, but I think for this episode, infinity is a type of singularity.
But a singular, like the existence of 0 implies that I can define some quantity that's 1 over 0, right? And that implies that I can define some quantity that can be infinite, and that's really the crux of what we're talking about here, right? Like,
right?
Can things be infinite?
But I think it's more than that. It's more that we can't define it. You can try to pretend that there's a thing.
No, like you described it as like putting it into your calculator, but you can also just think about this logically. Like, what happens? Like, I can when I try to divide 3 things. If I have 3 potatoes, right, I can divide it 3 times into 3 people, right, and I can even divide it more than that if I cut it in half, right? But like, what happens if I cut it into pieces that have 0 side? Then we get a problem, right? That's a singularity.
Right, but I know it's a little bit abstract, but I think that when these ill-defined things happens in mathematics, And a lot of times we just shrug our shoulder, like, whatever. Okay, the calculator
No,
broke.
in mathematics they pay attention to it. In physics we say, okay, that's such an extreme case. Okay, like when am I ever going to divide a potato into like size 0? Like I'm never going to do that. So who cares? Right? That's what we say in physics, right? In mathematics, I think people pay a little more attention to it now.
I'm not sure. I feel like in mathematics you can kind of work around it, but in physics you're kind of stuck. Like when math goes into real life,
Yeah.
you can't weasel your way out of 1 divided by 0. If it's really
But
1
that's the
divided by 0.
mathematician's job. That's their. I'm just saying that's their job, right? Like in physics, there are physicists whose job it is to understand these singularities, but nobody really cares. Like it's not like a building is going to collapse if they get it wrong. It's like society, like it's they have some freedom to just kind of I feel they have some leeway.
Yeah, yeah. I guess we kind of went off the beaten path on this discussion.
I think it's kind of related to this whole because it's an interesting question, like whether these singularities even exist, like where do they come from, the philosophical. I think it's a little off the beaten path, but hey.
Okay, I'll take it. I guess we've been throwing the word singularity. What is it actually? Because I feel like the mathematical conception of singularity is something that is infinite,
Yeah.
and then the physics conception of singularity is like the center of a black hole or something like that. So maybe we can like go work from there and talk about is that the only type of singularity? Are those even singularities? Like, yeah, just frame it in the context of this discussion.
Yeah, I think that's so. Like, I guess that was kind of I was trying to bring this idea that the singularity, in a sense, it's definitely tied to infinity, right? The concept of infinity. And people have a perception of that, from childhood as just being like the largest possible number that nothing can be bigger than. But if you study the mathematics of it, you can learn that there's actually many different kinds of infinity, and certain infinities can be bigger than others. There's like a hierarchy of infinities.
Yeah.
But we don't think about that in physics so much, do we, Tim? We don't think about like
I would say
these little puzzles don't matter to us, right?
I would say so far in the history of humanity, every single infinity that physicists have seen turn out to be not real infinities. They turn out to be fake.
Yeah.
They turn out just to be that, we did our math wrong, basically. Like, for example, in the case of like dividing potato by 0, let's say. Of course, if you really divided 1 potato by 0, you get infinitely many pieces. But like physically, you can't do that. The smallest indivisible thing is like, I guess imagine an idealized potato. It's made of it's made of carbohydrate, right? Like the smallest thing, it would just be the individual molecules. So the most you can divide it by, it's like 1 atom at a time. So when you do your homework a little more carefully, you realize that, hey, physically, a potato can be at most divided by, I don't know how many atoms, but like a very, very large number of atoms, but no more than that. Like that's the end.
You're trying to take your theory to a place where it doesn't apply anymore, right? Like, and you have trust in it, right? But you realize below the length of whatever carbohydrates or starches, that concept stops making sense.
Yeah. So okay, that makes sense to me. Then I guess to flip the script back at you guys, why are we even doing this episode if singularities are just sort of like these I guess I don't know if I should say quirks of a theory that just happen to be we can't explain it.
We don't believe that they're physical. We don't believe that they actually exist. But then I was talking to Tim yesterday, and I don't know anymore.
Well, I think
maybe.
Oh no!
I think a little bit of history is required, right? Like so Einstein first wrote down the general theory of relativity, the equation that says, hey, if you have matter, the space-time is bent, and then the matter will react by following the space-time, the curves. And then very soon later, I forgot what year it was in, like Schwarzschild came up with this solution, a black hole solution, and people were kind of shocked, right? They were like, hey, like this solves Einstein's equation, because Einstein's equation is really tough, really hard to solve. And Schwarzschild came up with this solution, and it's the simplest black hole solution. And And this solution has a singularity. The formula is at some point literally it's like 1 divided by the radius, right? It's literally 1 divided by 0. So somewhere in the solution, you're dividing by 0. And then I think there was a debate, and people kind of like, this can't be real. Like, like physics does not tolerate infinity. Just like you cannot divide a potato by infinitesimally small bits. So the black hole at some point must not contain 1 divided by 0. Yeah. But then there were some questions on, maybe this solution is too idealized. Maybe it's like a spherical cow. Like there's a joke that says, if you look at how a cow walks, people approximate it by a sphere. But that's clearly not what a cow is. So in the same vein, a black hole is not like a sphere. But then Schwarzschild's solution is saying that a black hole is just a sphere. But like, real world cannot be that perfect. So there was this question of maybe, hey, look,
is the devil in the details?
Right, exactly. Yeah, maybe this black hole is just too darn perfect. That's why you're dividing 1 by 0. But slowly but surely, people actually come up with more elaborate solutions to Einstein's equation. They got black holes that have charges, black holes that are rotating, but still, these are kind of like fancy black hole solutions, very particular, right? But then, I think fast forward many years later.
Seems like the devil's not in the details.
Right. So exactly. So Penrose, is it 1960s or something? A mathematician by training, I think, but he's also kind of a physicist. He actually proved that mathematically as long as you have matter that's like reasonable, it will form something kind of like a black hole. We will cover what the details mean. So that these sort of singularity, at least in terms of mathematics, turns out to be inevitable. And Stephen Hawking and Roger Penrose, with the joint forces, they further refined this. Basically, the statement now is that forget about black hole. If you just have stuff in a universe, the statement is that there are unavoidable singularities one way or another. So it turns out that Einstein's equation just gives you 1 divided by 0 one way or another. It gives you singularities. So that's sort of where we're at right now.
I also want to, I guess, Tim, can you also talk about like, gives you singularity? Is it in a finite amount of time, an infinite amount of time? Like, if I just kind of wait infinitely long, would there eventually be a singularity, or is it like?
Yeah, I actually had the same question too. Yeah, like, so is this just a function of the fact that if we wait an infinite amount of time, things are eventually going to collapse? Like, is it just kind of trading that infinity for like?
Yeah, so I look at some details, but not fully because it's quite complex. I think the answer is that the crux is that you don't have to wait forever. That the singularities do happen. But we'll go through details. Like
everywhere, like just
right.
Everywhere.
Yeah. Like for example, if you have something that's blowing up, I don't know, like the national debt or something, you might say, you can wait eternity, it will never truly blow up to infinity, right? But that's not how it works in space-time. It tells you that at some point in the past, you could get there, or some time in the future, you could get to this singularity. It's like falling into a black hole. Not to the people outside, but if you choose to go into a black hole, at least mathematically, because we don't know truly what happens, you will hit that singularity, even if you survive passing through a black hole. Like, you will hit it. Like, a minute, 2 minutes, 3 minutes, like, bad things will happen to you. Like, you don't have to wait eternity. So yeah, these are actually physical. If you just believe in Einstein's equation, these are physical singularities that are actually cannot fully be avoided.
Interesting. So why don't we go through it? Let's I guess I'm going to preempt the audience with mentioning that there are like three types of singularities, one of which we outside the scope of this discussion, which can maybe loosely touch upon, but maybe we can start with the first two. You pick whichever one you want, Tim.
Yeah, I think the most familiar type of singularity is probably those from a black hole. Yeah, basically.
Okay.
And this is Penrose sort of original argument. Basically, if you just look at matter floating around in space, because gravity is attractive, so things floating in space, as they move in space and time, they will slowly kind of converge, right? Now the idea is that the more they converge, the stronger the attraction is, and by proof by contradiction, it says that, you know, if you assume that these stuff in the universe, basically the crux is that at some point they collide. They have to like converge into an infinitesimally small space, and all hell breaks loose. Like you can't stop that. It's inevitable. You can maybe save it so that you can extend their lifetime, but at some point, eventually, they will all converge. Enough of them will converge, and we believe when that happens, you have something like a black hole. It becomes so there's so much convergence that becomes inescapable, and that was proved mathematically. You don't have to solve for the Einstein's equation, like just raw mathematics show that this will happen. So that's I think the simplest version. Yeah.
Yeah.
Can I ask a question that might be like a little bit technical, but I can also tell a story around it, I guess.
Only if you tell a story.
Yeah, for sure. Yeah. But it's mostly the story. Yeah. So like, you know, Sahil, you'd mentioned earlier how like or alluded to the fact that like most physicists, when they see infinities, like we don't really take them seriously. I guess like one reason is as we discussed, because of the fact that they don't typically concern questions that involve like near-term technology advancements. So like they're not like, you know, it's not worth spending money to try to invest in understanding the singularities. I guess the main reason they don't get a lot of attention. But also because historically, when we've seen infinities and singularities in equations, we've like just it's like there's a historical trend where in hindsight we've realized, oh, that wasn't really an infinity. Like we were being silly about how we applied the equations. And I guess one of the most stark examples of that is a lot of people may have taken electromagnetism, so they understand that like if you have an electric charge, there's like an energy density around that charge, and that's contained in the electric field. And the energy density behaves like 1 divided by the radius, meaning the closer you get to it, the stronger the energy density of the field. And that equation has a singularity, like when it's 1 over the radius. So if my distance to that particle goes to 0, then the energy density I feel should go to infinity, right? That's what that's what Maxwell's equations tell us. And then of course the resolution to that is, you know, when you actually get close enough to do the experiment, you discover quantum mechanics, you discover that there's a pair creation of particles and pair annihilation of particles that creates a screening effect that effectively shields the charge so that you don't get this infinity. But I think what Tim is saying is like, you know, even as weary as physicists are about like these fake infinities, these things that are masquerading as infinities, like it's different, right? And what I want to ask, I guess the technical part of this question that I wanted to ask is like, Tim, because you've read more into this than I have, particularly recently, but like how much would you say of this is attributable to the fact that like gravity is purely attractive, right? Like with electric charge, you have a concept of neutrality, right? Like I can create neutral pairs of electrons and positrons out of the vacuum, right? But and that's going to create some kind of neutralizing effect. But in gravity, I don't have this option, right? Everything is attractive, and so attraction just builds on attraction. It's like this positive
Yeah,
feedback mechanism, right?
I think that is the crux, and it's a really good analogy to compare gravity to electromagnetism.
Yeah.
Like Mikey, like you said, you can argue that there's a singularity in electromagnetism, but we don't worry too much about it because if you an electrician, you don't really have to worry about that because things average out. Like the positive, if you have positive charges, negative charges, the singularity kind of cancels out a little bit on average. Yeah. So if you zoom out, you actually don't need to worry about how the singularity resolve itself. They kind of just like smooth out. Yeah. And in the same,
I love it sometimes when there's like a mess in my apartment. I'm like, it'll solve itself.
Yeah.
It'll fix itself, right?
So yeah, so in physics, in most circumstances, minus gravity, you know, like you might encounter infinities here and there, but like they're not a big deal. But gravity is unique in that because it's purely attractive, the singularities become unavoidable. You know, like if you have two black holes next to each other, the singularity doesn't cancel out on average. They add up together, right? Because they're purely attractive. You have more singularity, right? And another type of singularity is the Big Bang. You know, it's a singular point where is, at least according to Einstein's equation, is at infinite density. You can't just ignore that because everything comes from the Big Bang. So gravity has this feature where it creates singularity, but on top of that, those singularities are not avoidable. You can't smooth it out. Like you have to, like it forces you to confront with it. I think that's what makes it kind of more significant and different from some of the singularity we've seen.
It feels to me like a really sour candy that just makes you like, it just like sucks. It just wants to suck itself in. I don't know.
Yeah, I guess I want to kind of dig deeper into this. So right now we're talking about more spatial singularities, like those, you know, found in general relativity in a classical black hole. But wanted to ask the you know, the question, like, what if you had an empty universe, which is a single like proton or something with the mass of a proton? Size is irrelevant at this point because it's the only object in this, like, and let's say the universe is infinitely large. Would you still get a singularity?
Yeah, and I think this is sort of the following up work, right? So initially, Penrose theorem is just deals with black holes. Like if you have matter and there's nothing, there's no expansion of the universe, slowly the attractive force would just kind of converge things, right? But then I think Stephen Hawking kind of take it a little bit further. Look, I don't know who to properly attribute credit to, but it is what
Fair
it is.
enough. Fair enough.
But basically, if you don't have the space-time that's expanding for the moment, then eventually the space-time, because the gravity will react, it will shrink because there's gravity, right? And the shrinking will cause space-time to collapse. Maybe it's not like a black hole, but basically, if you live in this space-time, eventually your life will end, basically, one way or another. Like there's no, like if you're just floating in space, you're like imagine everything in the space-time has like an invisible train track, just like where they're going, kind of. This train track would just end, and I don't know what the ending is, a cliff or something, but like you don't get to ride on the train all the way to the sunset, around and around. You don't get to do that, right? It ends, right? And now let's say you try to dodge it, but like, oh, you know what? My space-time may be expanding so that instead of everything converging and collapsing, let me expand that. Well, if you follow that logic, if you go back in time then, because the equation works forward and backward, then your singularity becomes back in the past. Then you have a scenario like the Big Bang. So one way or another, you either have something like a black hole, you have like a Big Bang or Big Crunch or whatever. It's
like a seesaw. Like you gotta like, if you try to beat it one way, it's gonna get you
right.
You can't avoid it.
I think the thing is, like, gravity just doesn't like to balance itself. It's like
it doesn't. Yeah, it likes to eat itself. It seems.
It's like a very self-destructive force, basically. It doesn't like to be stable. Like one way or another, something gives.
Yeah, I mean, like, right, like people have these notions of like yin and yang and balance and charge is plus and minus and like gravity is like a different beast, right? It's just
Mhm.
like it's just one way and it's unique in that fact. And I mean, a large part of our existence is owed to that. So what does that mean for good and evil? I don't know. I should follow it up at the end.
Yeah, I mean, I do want to give other somewhat related examples, right? Like, I don't know if our audience knows, there's a famous Millennium Prize problem called the Navier-Stokes equation. It's supposed it's a simplified equation that governs how fluid works, like water flow and whatnot, right? And people thought, this equation, when you have water running around, maybe it'll form vortices and whatnot. So the Millennium Prize problem was to show that, well, people believe that because it describes real life fluids, that it should not have singularity. So the Millennium Prize problem is to either prove that there's never a singularity or provide a counterexample. Right? Although no one has solved it, right? It showed that but people generally, I think, believe that the equation is stable. Like it doesn't create, it doesn't destroy itself, and it makes sense because if you have water fluid, like water molecules, sure, they on some level they're attractive, but they're also repulsive, right? Like water molecules bump into one another, they will repulse. So there's some level of balance. But
Notion of balance.
gravity is different, right? Like you take Einstein's equation for gravity, and lo and behold, it just collapses onto itself. Like that's weird. I just want to emphasize how weird that is. Like it collapses.
And it's funny because oftentimes we like to think of space-time, not necessarily as a fluid, but as some kind of fabric in the least, right? And some kind of fabric that you could kind of imagine it obeys differential equations, and so you might sort of think it's not that different from a Navier-Stokes equation. And I guess it's the incompressibility of Navier-Stokes that probably
a little bit, probably, yeah, probably stabilize. Although no one has proved it, let me put it that way. But still, like it's less contentious. But like gravity, it just gives you singularity. There's literally a solution that has a singularity. Like holy crap! Like that's not.
It's like a balance with no checks. It's just I can just.
I guess I really want to give a I guess kind of an analogy to how to think about space time, because at least initially the way I would think about it is like, say you have something that is a very small mass, not enough to collapse on itself and form a black hole. Like I believe that's what's called the Chandrasekhar limit of like being some multiple of solar masses that's greater than one, like something greater than the mass of the sun in like a small enough space, and then you get it eventually collapses in a black hole. But I really want to talk about like the case where you have like something very small, just single proton, just hanging out, no other charges, nothing else, and how space-time itself will eventually collapse. And really like, because space-time is infinite, you would think it would take an infinite amount of time for it to like eventually collapse onto itself, but you're telling me it's actually a finite time, which is surprising. So, I mean, I want to think of different ways to visualize space time. One way I'm thinking about is kind of like those toys where they like expand, like as you pull it, like everything just kind of expands out. I don't know if you know what I'm talking about. Like they like become really small and they become this like huge ball as you pull them out, and it's like it becomes
those those sphere things that like
yeah. So
cool.
is that an apt analogy, or like how do I think about it becoming like small in a like, or literally zero size if I ignore like if I assume general relativity is like 100% correct, forgetting about quantum effects and stuff like that. Give me a way to visualize it.
I know it's a little difficult, but probably the best, maybe the most intuition is like think about Big Bang, like our universe.
Wait, I just want to chime in here real quick. Well, one of the things that Sahil said was that the universe is infinite, so it wouldn't take an infinite amount of time. But I think that's kind of the key. Like if that was true, you'd be right. But there is a Big Bang, as Tim just alluded to. Like we shouldn't really think of it as being an infinite space. So there is like and then I guess Tim can
I mean I know that you are comparing infinity, but basically if you look at the Big Bang, let's say you can subscribe a size or some sort of density size to the
Some
universe.
metric, some meter stick. You have a meter stick after the Big Bang, right?
Okay.
Let's say the meter stick is 1 meter right now. It doesn't matter what, 2 meters, 5 meters, right? Basically,
Sure.
if you go backward in time, that meter stick eventually shrunk to 0. Not just like if the meter stick shrunk to like 1 millimeter, yeah, then you don't have a singularity. It just got small. But the crux is that if you just ignore quantum physics, because quantum physics probably will rescue that. But if you ignore quantum physics, Einstein's equation tells you that that meter stick, that's 13 billion years ago, doesn't shrink to 1 millimeter or 1 Planck length. It shrank to exactly 0. So all meter stick everywhere in the infinite universe got shrunk to 0. The whole thing collapses to nothing, right? So that's a real singularity. So it doesn't matter where you are. It's just
Yeah, I'm still trying to understand this, like a way of kind of visualizing this, because let's imagine the Big Bang didn't even happen. Let's just say you have a single proton sitting in this toy universe. It's just there, just hanging out, and you have this like all this space time that's empty. There's no quantum fluctuations because this is a nice smooth picture of the universe, completely geometrical. Why will it collapse into a singularity like in a finite amount of time?
right.
I
Because
mean, so yeah, like no Big Bang, no expansion of the universe, just you take one snapshot in time. I assume it would be infinite, right? Is it presumptuous of me to say it's infinite? Like, does this theorem not apply to infinite size universes?
no,
If it's
it
finite,
does.
I can understand. Yeah.
No, it does. It does apply to infinite universes. And the
Okay.
fact is that, if the universe is not expanding, the size of the meter stick eventually will collapse in the future. Because there's matter and the universe is slowly shrinking. Or if the universe is expanding, you extrapolate backward in time, then that means the meter stick used to be 0 at some point. So either way, you can't dodge it. Yeah.
I guess I'm trying to really get to the thing of what a meter stick means in this context, because I can't. I mean, are you telling me like if I had if I had a proton and this like let's say meter stick that didn't really interact with anything, kind of this like invisible fictitious meter stick, that the meter stick itself would shrink, like
Yes.
actually would compress down and
I'd say
like
that is the best way of thinking about it.
Yes.
okay.
That's the best. That's the most accurate model for
Yeah.
describing the physics.
Yeah.
Yeah, it's kind of interesting, right. And that meter stick we call the metric, right?
Yeah.
So there's actually mathematical logic behind it, and it can literally you can analogize it to a meter stick, and
Yeah. So the meter sticks will spontaneously get closer and closer to one another, and also be smaller and smaller and smaller. So even though you have infinitely many meter sticks everywhere, the singularity happens when they get so close. Eventually, they all they are all everywhere, but they're also nowhere because they've disappeared. So that's
all general relativity is the law of meter sticks.
Makes sense. Makes sense. I guess I want to kind of ask maybe a pseudo mathematical kind of question. So, if you take a universe that's infinite size and you're telling me through this process, it can essentially become 0 in a finite amount of time, does that mean that the function that describes like how it's like shrinking in size is like beyond exponential is just like uncomputable, or like what, like how do I think about this?
let me just say
The only function we have for describing the size is the function of this imaginary meter stick, right? If I'm not mistaken.
Yeah, I think so. Yeah, but let me emphasize that yeah, so we're trying to understand this particular scenario, right? But the proof from Hawking and Penrose, these are abstract proofs. They just say, oh, mathematically, if you live in this imaginary space-time, your life will end. Doesn't matter how long you live, it will end at some point. But in this particular situation, yeah, we can understand why, because like the universe literally will shrink to nil. Like that's when everything ends, right? But generally, you don't know. But that's why the theorems are powerful. It tells you don't have to know how the universe is changing or expanding. One way or another, they end. So.
I think maybe like correct me if I'm wrong, but maybe what you might be alluding to, like there's interesting philosophical question, right? Like if we just doubled everything in the universe, like doubled, all the constant, maybe not doubled, but some proportionate, if we just increased everything, like would we even be able to tell? Like, the speed of light was increased, electric constants, like we'd just be bigger, but we wouldn't have any understanding of what that even means, right? But like the
Yeah.
singularity thing is beyond that. It really points towards the destruction of all of this. Uh,
Hmm.
yeah, it's not something that happens smoothly. It's very catastrophic.
Yeah. So
As we
so
I
see in
see.
the real examples, like the black holes that we observe, they seem very catastrophic. We see them eating stars, and something's going on
Mhm.
there.
Yeah. That makes sense. So far I know we've talked about singularities in space, um, like centers of black holes, the Big Bang. At least if I visualize like turning the clock backwards and watching the universe as it shrinks, and if you go forward, it expands out. What about singularities in time? Like, what does that even mean? Because time seems like goes from zero to infinity or negative infinity to infinity, zero
yeah.
to infinity.
Yeah, I mean, well,
What does singularity in time
this is
even mean?
actually the audience question that inspired this question originated here, right? Because
Uh,
we know that the educated viewer pointed out that relativity tells us that space and time are the same, so you
mhm.
can rotate one into the other, and we can't really think of them as separate. And so if space must have had a beginning, then time must have had a beginning. So yeah, Tim, what's the deal with that?
Yeah, Tim.
Well, I mean, the difference between the two singularity is just the position in space time, right? Because we know we have three space dimension and one time dimension. So a
Mhm.
singularity in black hole is localized in space but spread out in time, right? It means that, let's say today, um, let's say today, if I'm at the singularity, the location, well, then I'm doomed. And tomorrow, if I'm at the location with singularities, I'm also doomed. But I could theoretically walk around it in space.
Black holes have a permanence. They exist
Yeah,
through many different time slices, right? So yeah, they're
exactly.
like singularity for that reason, I guess. Is that what you're saying?
Yeah. So you can dodge around. So black holes are
They,
space like singularity because you can kind of dodge around it by walking around it in space, but you
that's
cannot
basically
dodge.
like, is it dodgeable?
Dodgeable, right? But the Big Bang is not dodgeable. You can only dodge it by being in a different time.
Yeah.
Right. So I don't care where you are. You can be 5 meters in front, back, left, right. Imagine that meter sig. It's just shrinking, and whoop, nothing. Right. Like it's not dodgeable. It's like doesn't matter where you are. It's almost like imagine if you're in a simulation. It's like the server getting turned off. Like there's no more meter stick. There's no more game
Yeah.
to play. Like everything is
Yeah.
shrinking to nil. The only way to dodge is just go to a different time, right? So black holes you can dodge by going to a different space, but you cannot dodge it by going to a different
Right.
time. But
Mhm.
Big Bang you can dodge it by going to a different time, but you cannot dodge it by moving to a different space. So I think that's sort of the
Mm.
distinction.
Yeah, so like I guess to address the viewer's question, it's like, yeah, so it's true. Relativity tells us that space and time are connected. I can like, in a sense, I can turn my head and a place that looked like space and it looks like time. Space-time is basically a blob. Some parts of it look like time and some parts of it look like space. But when these
Mhm.
singularities happen, I guess there's two kinds. There's the inevitable kind, like it's like Thanos. It's like just inevitable. And then there's the kinds you can dodge. And that's determined by the geodesics of the space-time and the geometry. But like that's really what it comes down to, isn't it? I guess. Is it dodgeable?
Wait, Mikey, jargon alert. You said the word geodesic. The hell
Oh
is
yeah,
that?
yeah. Oh, I just mean just the lines that like so yeah, a geodesic is just a technical term. Like when you're talking about like the proton in the universe, like just the line that it traces out through space and time, right? Like so when we're talking about
Mm.
singularities, we talk about the fact that these lines all inevitably seem to like shrink
Converge.
get sucked up into
Yeah.
one location. Yeah. So
Yeah,
these,
Mm,
yeah, we call them
I,
world lines, but we can also call them geodesics in this context. Yeah.
I think a
I see.
good analogy is like an invisible train track. Basically,
Yeah.
the
Mhm.
theorem proves that these invisible train tracks eventually collide.
Well, that's
So
a very deterministic viewpoint. I get we're all on invisible train tracks, right? And that's a very deterministic Einstein, like classical GR view of the universe. But that's what we
and
just
yeah,
Oh, go ahead, Tim. Sorry.
and also on a collision course. Maybe in the past, in the future, in somewhere in space and time, but there was a collision at some point, basically.
Mhm.
everything intersects eventually. That's kind of poetic,
Mm.
isn't it?
Yeah, that's essentially the theorem, right? There's an intersection of all these, so they have to end, basically.
I see. I see. Could we touch upon really briefly? I mean, I kind of take it for granted at this point, but maybe like one or two sentences of how space and time are like one and the same, why they're not separate from each other,
Ooh,
in the context of this discussion.
Yeah,
one or two
because
hard.
on
It's the
some
most counterintuitive thing that.
What's up?
Huh?
Would you say, Mikey?
Well, it's the most counterintuitive thing that I can think of. So one or two sentences is hard, but I mean, Tim sounded like you were going to give it a go. Let's see what you got.
Yeah, I mean on some level, space and time can kind of convert into one another because of time dilation and length contraction. But you have to know a little bit of relativity to see that. Like
Yeah.
if you're traveling very close to the speed of light, certain amount of space become compressed. But then like
Uh,
time also seems like it got slowed down, whatever. So you can think of it as a conversion between space and time. They can convert to one
mhm.
another to some extent. Yeah.
Yeah. Well, okay. One of the good analogies I heard once, and it's just obviously not an exact analogy, but just to give you a sense, it's like imagine you have a car whose top speed is 60 miles an hour,
Mhm.
and I'm driving due north. Then I'm driving 60 miles an hour north, right? But then if I start going northeast because the road, you know, dictates that I go that way, my
Mhm.
travel through north in the northern direction will be slowed down, right? Because some of it is diverted towards the easterly direction. And space and time are connected in very much a similar way to the point where
Mm.
if I'm moving through space, okay, all my motion is going through time. So it's fine. We experience time the same way. But if I start traveling really fast, now some of my motion is diverted through space, less of it is there to go through time. So my time slows down.
Oh,
Yours,
I
yeah.
see.
So
Is this just to refresh my own technical memory? You're talking about like space-time interval and stuff, right?
yeah.
Yeah.
And
Oh, okay.
it's a
Okay.
rotation. It's so in for the northeast example, it's a literal two-dimensional rotation. For
Yeah.
relativity, it's a hyperbolic rotation. But for all intents and purposes, it's the same thing. They're sharing
Yeah.
resources. So the more you go through one, the less you can go through the other.
I see. I see. Okay. That, I mean, to me that makes sense. Yeah. So I wanted to, I guess Tim, maybe I know we said this is out of scope, but maybe we can briefly touch upon the third type of singularity. Just maybe how weird it is, and then we can maybe dedicate an episode to it if it tickles our fancy.
Yeah. So we talk about how to dodge some of the singularity.
Mhm.
So there are these space-like singularity, right? Like you can kind of walk around it.
Mhm.
And there's these time-like singularities. So maybe you can dodge it by being at a different time. But there's a
Mhm.
particular type of particle that doesn't experience space and time in the same way, namely a particle
Mhm.
of light. If you move at the
Mhm.
speed of light, you can argue that time freezes for you,
Mhm.
because you don't experience time because you're moving at the speed of light. You can never be slowed down. So this kind of a
Mhm.
question: what if you move at the speed of light? Can you, in according to your point of view, can you dodge the singularity? I think the answer is still no. There's this.
Well, no, that's the test, right? That's why people draw a Penrose die because, like, if you can't dodge it as a beam of light, then you can't dodge it, right?
Yeah,
So, like, that's
basically.
why Penrose diagrams are useful.
Yeah,
Uh,
so there's a third type of singularity, the null like singularity, where the singularity happens in the speed of light direction.
Yeah,
But that
right.
but that's very, I think that's very unintuitive. I don't even know how to think about it personally. But there is such possibility, but it's neither black hole or Big Bang, but something like that could exist. We don't know what that looks like though.
I see. I see. Uh, okay. Okay. So I guess coming back to I guess one of the points Mikey made on a more philosophical side, or maybe more pragmatically speaking, whenever physicists see singularities, at least my interpretation of it is like, oh, the theory is broken and it doesn't explain this regime, so there's something else that supersedes it in this in this limit. And so if that's the case, like, is it even useful? Just if there's no such thing as a singularity, does like if it's not physical, then like can we explain this in the context of that?
I can give my perspective just first as a
Sure.
skeptic because, like, yeah, like that. That was my. But then after talking to Tim, like, when you realize how these singularities seem to be of a slightly different nature and how unavoidable they are, like,
Mhm.
it does start to give me like a little bit of discomfort. Like, I still believe that there's no singularities. I still
Mhm.
believe like something will come in to save the day.
Mhm.
But it's definitely something to raise an eyebrow about.
Yeah, I just want to add one thing real quick, Tim, before you comment in, is that like all this talk of singularities being inevitable is based on Einstein's theory of relativity, which we definitely know is incomplete. So I'm wondering, like, clearly, in quantum mechanics, can you make the same argument that like singularities are inevitable, or just curious your take on that.
Yeah, I think certainly it's definitely an open question, and people believe. I
Mm,
think it's still under debate, right? Like even if you have quantum
mm,
physics, might there still be singularity? I mean, it's possible. It's possible. Our quantum theory of gravity is incomplete, so we still see singularity. But then the question is, when we have a quantum theory of gravity, would there still be
mm.
singularity? That's still a bit of an open question. I think physicists like to believe the answer is no, because
Can't be.
historically there's no such thing as singularity, right?
The entire practice of particle physics, the entire practice of modern quantum physics is how can you get rid of infinities? So if you're saying that maybe there's just an infinity there, it means that we just lost the battle.
But I would say the infinities in gravity is like the hardest ones to get rid of.
It is definitely the final boss.
Yeah, but
Definitely.
but but I want to give the audience a flavor on why like it's a bigger deal in gravity. These
Yes.
singularities, right? Like
Uh-huh.
like we said before. Like imagine I'm trying to study water waves. I don't need to know quantum physics to study water waves, right? The effects of quantum physics are kind of washed out and when we average out. So there's this averaging effect where if I have singularities, they kind of don't matter so much. And if you try to apply the same thing to gravity, you actually can't. I mean, sure, you can say that, oh, if I'm just
It actually
studying,
works.
I, I mean, it, it, it worked to the extent that you can, if you just ignore the elephant in the room, like imagine you just,
Sure.
like,
But if you don't, it makes it like makes it exponentially worse. It like makes the problem worse.
yeah, but so basically, like,
It causes the lack of. I think it all comes back to that lack of neutrality, right?
yeah. So like, sure, if you want to study rocket launch and whatnot, you don't have to worry about quantum gravity. But the elephant in the room is that our entire existence comes from the Big Bang, which is a
Mm.
point of singularity. Like, unless you totally just ignore almost what your Carl Sagan said, right? Like, if you ignore the fact that the universe was created, then sure you can study rocket launch and you can make an apple pie. It's fine. But like, our universe comes from this singular point. So without truly understanding the physics of the singular point, it's almost like there's always this knowledge gap. Like, what happened? So that's why like it's a lot more inevitable in the gravity case because you can't like just cut it out of the theory and just kind of and just ignore it, right?
Yeah.
Huh. I'm wondering, I guess, so you don't see this for any of the other forces, only for gravity because it's universally attractive. I, I I guess I'm just kind of wondering that, like, I mean, even in the case of black holes, like, we don't know what's inside a black hole, so there may not even actually be a singularity, but it appears from the outside as if there were a singularity inside. And so I guess I'm just curious, like, even with Big Bang, like, we're just like, if you were to naively run the clock back all the way to like the beginning, we'd say, oh, it's like a point, but we don't know if that's actually the case. And so,
I think one way to
yeah.
describe is what Tim is trying to say about the inevitability is like, like going back to the potato analogy, right? Like if
Mhm,
I could divide a potato, right, like into
mhm,
like a billion pieces, I know I'm gonna reach some limit here, right?
mhm,
Because there's starch molecules, and then if I'm breaking up the starch molecules, can I really call that a potato? Um, and I think, yeah, this isn't going to be like the entirety of what he's saying, but a big
mhm,
part of it is like in the physics community, like every attempt to try to reason something like that, like, oh,
mhm,
maybe there's like some like fundamental building block, maybe there's some like minimum like Lego, like imagine the whole world's made of Legos, and you have like the Lego side,
mhm.
and that's like every attempt to do that has come up short and has ended up not making sense. So in a
Yeah.
sense, it's just like I said, like I think to a large degree, it's fair to say that the entire field of modern physics is like trying to figure out like
Mhm,
how modern particle physics is how can we explain these infinities and show that they're not really infinities there. But with
mhm,
gravity, every attempt to do that has fallen on its face, completely failed.
mhm.
And so as physicists, we think that that's a sign that maybe there's something actually special going on here.
Mhm, mhm. I see. I see. I guess I wanted to maybe kind of I guess change the tune of the conversation, take the other side. Like, what if there are singularities? Like, just what does that mean for physics? Like, what if it's just inevitable? Like, actually, like quantum gravity and all, like there exist singularities, and that's it. There's nothing you can do to get rid of them. What does that mean?
That would just be a really weird thought because every
No, it'd
like
be the end. It would be the end of predictability. It would be the end of predictability. So yeah, like you could say, yeah, like literally, maybe we're all part of a simulation, and if you actually look for where the source code came from, like the hardware, you might get some nonsensical answer like an infinity, and that just
Uh-huh.
means that like we do not have access to those answers. Like I I think that's what it means, right? It just means that those answers are inaccessible to us.
Hmm.
because it like his physics. One of the goals of physics is trying to make predictions from the past, right? To say, hey,
Hmm.
because of A, B happens. But the
Hmm.
thing is, if we trace our past all the way to the Big Bang and we find out that it's a singularity, it's something that's ill-defined,
Hmm.
then like what is the starting point of our universe? Like what are we
Hmm.
like did we just get something from nothing? Like
It's almost like
single
yeah, it's like a cheat code. It's like if oh shit, if there's like a singularity in the universe, and I can just grab all the energy I want from that.
I,
Like
I, I
nothing.
I guess you can kind of blame, then inevitably you can kind of blame the singularity. But like, oh, I made some mistakes today. Well, I mean, who knew it was the Big Bang? What can you do, right? Like, it's almost
It, it,
this, yeah.
it's oh man, that's actually because I was gonna say it's almost like a scrambling machine, but like black holes are also kind of like scrambling machines, and it's related to their singular nature. Like a singularity would mean yeah, you can like do whatever you want. You could like murder a bunch of people, like, and you just throw in the singular, and no one will ever. It's like just erased. Like it's like you can't trace it after that.
Yeah, and I guess the question is, where do we come from? It becomes then we don't have an answer. It's just
Yeah,
singularity. It's just
yeah,
a point of nothing. I don't even know if you call that a point. It's just
yeah.
undefined, right? Like
I
that's
what? Okay, what about this? Like, okay, I'm gonna throw some really speculative stuff at you guys, and just in the context of this discussion, what about kind of like the thought process of like, oh, like there's this empty space, and then with enough time, a certain quantum fluctuation happened that produced like, I don't want to say an explosion because that's not actually what the Big Bang was, but
Like a
something
Boltzmann
akin to
bracket?
a Big Bang and just gave us everything we have, like out of
Yeah,
nothing.
yeah.
So I'm curious, like from that context, is that a singularity? Like, what would
Well,
you consider that?
if you make that work, then it will be resolving the singularity, right? Then there will be no more
Hmm.
singularity, I think.
Well, yeah. So like, so what you're asking is like a very quantum mechanical question, and what we're talking about is like very, very like classical general relativity, right? So those are two separate. But if you were to combine those theories in the most naive
Hmm.
sense, what you described, like the sudden fluctuation of like, something just materializing out of nowhere, that would create a black hole in classical general relativity that would just create another singularity, right? So
Yeah.
it's this like point, it's like a place where you can't extract any answers from. And it's
So
just
is it like once you have a black hole, then it just will just create more of itself, basically?
yeah, exactly. Yeah, yeah. It keeps on feeding itself, and you can't get any answers out of it. And so
Uh,
that's why modern particle physics is entirely dedicated towards trying to battle these objects because they represent our inability to extract information.
And and
I
and I,
see.
and I wonder
Hmm.
if you can come into this situation. Let's say you have an explanation, and maybe if it's not fully quantum mechanical, you might apply the same logic and say that, well, that situation might lead you to another set of singularity, and maybe that
Hmm.
it just keeps going. Of course, you could have, I don't know, maybe one singularity in the middle that get resolved,
Hmm.
and then on both sides there's no more singularity. But that seems probably not. I mean, this is kind of like Steinhardt's rebounding universe idea, whatever. But then
Hmm.
the question, I mean, the question, it's a little bit close, like the question of God. I mean, I don't want to bring like theology into this, but like if you postulate that God created everything, like what created God? I mean, we're kind of in this realm now.
Picking the egg kind of. Yeah.
Like there's a
And no, like
singularity.
the Steinhardt thing is a good example because like you see people's like the smartest people's. I consider Steinhardt like on like the highest end like of respect intelligence. Like you see their attempts to try to like avoid this divide the potato problem, right? And
Hmm.
their best attempts are crap. So this is
Hmm.
a really hard problem.
I guess okay, this is my last and final question before we close this out. Is many episodes back we talked about how space and time are not truly fundamental. So when you get to a certain size, a certain very small size, then maybe the notion of space and time no longer make any sense at all. And so would you think speculatively that singularities in this new sort of way of describing things could exist?
That is our
Because
only hope. Like if I'm going on this thing of like describing like as an industry as a field of study, like our whole job, like Tim and I's whole job for 10 years is like, how do you get rid of these infinities? Like that's the only way. That's like our glimmer shining hope, whatever. Like the hero we hope will come save the day. I don't know. Feel that way? That's how I feel.
Well, I mean, that's almost a too hard a problem that no one really will tackle, right? The hope is
Well, me
that.
is tackling it.
Well, I don't think you direct. Most people don't directly tackle it, right? You hope that you might find it by accident, something
Yeah.
like a reformulation of what space and time is.
Nima's going hard at this angle though, right? That's why you gotta respect the dude.
But he's not. He's still not getting that close. I feel like, but who knows?
Yeah, but you gotta respect the effort.
So certainly, yeah. People who try to make progress in that front is it's hard. It's very hard. I mean, I personally, I don't think
yeah,
I can get into that, but.
yeah. No, we don't have to get too in depth. I was just kind of curious your guys' take on that. So yeah, we're almost near the end of the episode and want to give you guys a chance and our tradition with what singularities have taught you, any words of wisdom that they shared with you.
I
Share
still
with the
don't
audience.
believe in singularities. And Nima, please save us. Please tell us. Come on. That's all I gotta say. That's all.
I think it's kind of an like these sets of theorems are actually pretty interesting, right? Like they prove that our equations almost inevitably lead to like an identity crisis or midlife crisis, whatever you call it, right? It's
Identity crisis. I think identity crisis is more appropriate.
it's a little weird, for something as important as gravity. And but then when I'm thinking like, if I think like, what else would I have expected from gravity? This might be like the only sensible outcome because gravity is so almost contradictory, right? Like what else would I have expected almost?
Yeah.
You expect gravity to be all smooth and just some like simple fluid that's like a water flowing down the stream? No.
Yeah.
Like,
no, clearly, Tim. The reason why you and I think that way is because of the years of accumulated trauma.
probably.
That like normal people would expect that.
Yeah. So even though I think the results are unusual, like I expect nothing less from gravity. It is the big boss.
We should all
Yeah.
think of gravity as just a weird, crazy thing that we all are. Yeah, like if there's a god, it's gravity. Interstellar.
It's just weird enough that it's real. It clearly is beyond the imagination of people, right? Like if people were to create gravity, they wouldn't have thought so deeply about it, I would say.
Yeah, but we're gonna get it. Nima, come on, Nima, get it.
I don't know. Maybe it's futile. Maybe there's always some singularity.
I'm on Team Nima. He's gonna.
I like your thought process, Tim, that if we were to create gravity, we wouldn't have nearly thought as deep about it.
Yeah, we wouldn't throw singularities into the mix. I doubt we will, but
yeah, I just want to end this episode with something that you said in many episodes, Tim, that gravity is king. And then yeah, so
King.
On that note, yeah, what's up?
King and the queen, I think.
Yeah, okay, fair enough.
No, we use the word king in a all gender sense. Like it's not
That's
king
fair.
doesn't mean man. King, it just means the top, right?
Fair enough. I don't want to go too deep down this route. Anyway, so on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all.
Bye.
Bye.
It's fun. Oh, I gotta go, but